Welcome you all. Now we are going to discuss about design of digital filter using impulse invariant technique. Before that, let us see what is meant by infinite impulse response filter, that is IIR filter. So these are the class of digital filters whose output depends only on the not only on the current and past inputs, but also it depends on the past output. So by creating a feedback loop, so this recursive structure allows them to active sharp frequencies responses with significantly lower order compared to the FIR, and this makes them highly efficient. However, this efficiency comes at the cost of nonlinear phase response, which can distort a signal's timing and potential for instability if not designed correctly. So the infinite impulse response technique, it is a method for converting analog filter design to digital filter. It works by ensuring that digital filters impulse response is a sampled version of analog filters impulse response. So this is achieved by a direct mapping of analog filters poles from S plane to the Z plane. So at pole at S is equal to P in the analog domain, it directly translates to a pole at Z is equal to e to the power of Pt in the digital domain, where T is the sampling period. So what are the advantages and disadvantages of these one are, the primary benefit of this method is that it preserves the shape of the analog filter's impulse response. So this is particularly useful for applications where the time domain behavior of the filter is important, such as audio signal processing. And also the conversion process is relatively straightforward. It often involves a partial fraction expansion of analog filter transfer function and then applying the S in the Z mapping. The most significant drawback is that it has aliasing problem. Since the digital filter's frequency response is a periodic version of analog filter's response, so any frequencies in the analog filter that are above the Nyquist frequency will fold back into the digital filter's passband. So because of this, it distorts the frequency response, making the method unsuitable for designing filters like high pass filters, band stop filters, or any filter with a wide bandwidth. So what we can do in alternative to this impulse invariant is that we can use bilinear transform. So because of this aliasing issue, the bilinear transform is another popular and often preferred method for designing IIR filters. So it provides a more robust solution by using different mapping from S plane to the Z plane. So the transformation is based on the substitution of the S value. So how this is going to solve aliasing is that, so this transformation, it is actually a conformal mapping, so that maps the entire imaginary axis of the S plane onto the unit circle of the Z plane. So unlike the impulse invariant method, which has many to one mapping, the bilinear transforms mapping is 1 to 1. So this prevents aliasing because the entire infinite analog frequency range is compressed into the finite digital frequency range, that is minus pi to plus pi. So while the binary transformation solves the aliasing problem, it also introduces a different issue known as frequency warping. So the relation between the analog frequency and digital frequency is actually non-linear. So which means that the frequencies in the analog domain do not map linearly into the digital domain. So lower frequencies are mapped almost linearly, but higher frequencies gets compressed. So in order to avoid this, we are going to use pre-warping. So before designing the analog filter, the desired digital cutoff frequencies are actually pre-warped using the inverse relationship to determine the required analog cutoff frequencies. So this ensures that the critical frequencies like cutoff frequency in the final digital filter are precisely where they were intended to be. So when we see the properties compared to the FIR filter, IIR filter can achieve a similar sharp frequency response with a much lower filter order. So this makes them more computationally efficient and it requires only fewer coefficients and delay elements. So a significant drawback of IIR filter is that they generally have nonlinear phase response, and then the pole of analog filter in the S plane are directly mapped to the pole of the digital filter. So this ensures that the digital filter is stable if the poles lies on the left side of the S plane, and when we see in the digital filter, if the poles lies inside the unit circle of the Z plane. And then as I told already, it has aliasing problem. So because of that, we cannot design low pass, we cannot design high pass filter and band stop filters. An example for designing of digital filter using impulse invariant technique. So for the analog transfer function, for example, h of s is equal to 2 divided by s square plus 3s plus 2. Here we have to find the digital filter response, that is h of z, using impulse invariant technique, and we can use two timing, t is equal to 1 seconds and t is equal to 0.1 seconds. So given h of s is equal to 2 divided by s square plus 3s plus 2, so which is, when we take roots, then it becomes 2 divided by s plus 1 into s plus 2. So by partial fraction expansion technique, we can write this as a divided by s plus 1 plus b divided by s plus 2. So from this we can find the value of a and b. So the value of a is 2 and value of b is minus 2. Hence we can write h of s as 2 divided by s plus 1 plus minus 2 divided by s plus 2. By using impulse invariant transformation, we can convert analog filter into digital filter, and the transformation formula is ai divided by 1 minus e to the power of minus pi t into z to the power of minus 1. That is the sampling time. Hence h of z is equal to 2 divided by 1 minus e to the power of minus p1 t z to the power of minus 1 plus minus 2 divided by 1 minus e to the power of minus p2 t into z to the power of minus 1. So here pole values are 1 and 2. Hence we can write h of z as 2 divided by 1 minus e to the power of minus t z to the power of minus 1 plus minus 2 divided by 1 minus e to the power of minus 2 t into z to the power of minus 1. So when t is equal to 1 seconds, h of z is equal to 2 divided by 1 minus e to the power of minus 1 z to the power of minus 1 plus minus 2 divided by 1 minus e to the power of minus 2 z to the power of minus 1. So here we have to find the value of exponential terms, that is e to the power of minus 1 and e to the power of minus 2. So when we are finding the value, the e to the power of minus 1 value is 0.3679 and e to the power of minus 2 value is 0.1353. So after finding the value, substitute it instead of e to the power of minus 1 and e to the power of minus 2, and then we can cross multiply this, and then we can find the value of h of z in terms of z to the powers of negative powers, or else we can find it out by the z powers in positive also. So when the answer for h of z is 0.4652 z to the power of minus 1 divided by 1 minus 0.5032 z to the power of minus 1 plus 0.0498 z to the power of minus 2. So alternatively we can find it in terms of positive values also. And then when t is equal to 0.1 second, 2 divided by 1 minus e to the power of minus 0.1 z to the power of minus 1 plus minus 2 divided by 1 minus e to the power of minus 0.2 z to the power of minus 1. So here also we have to find the value, exponential values. So we are finding the values and then substituting it in the equation, then cross multiplying it, and then further simplifying it, we will get 0.1722 z to the power of minus 1 divided by 1 minus 1.7235 z to the power of minus 1 plus 0.7408 z to the power of minus 2. Or else we can find it out in the positive square values of z also. So the conclusion is that, so when we are using impulse invariant technique, the aliasing problem will occur. So in order to avoid the aliasing problem, we are going for the FIR filter, but a FIR filter has the problems like pre-warping, so it has to be avoided. So how we are going to avoid is that we are using s is equal to 2 by t z to the 1 minus z to the power of minus 1 divided by 1 plus z to the power of minus 1. So with the help of this one, we are avoiding the warping problem in the FIR filters. So FIR filters is most suitable for designing all frequency selective filters like low pass filter, high pass filter, band pass filter and band stop filter, whereas impulse invariant technique, it is best suitable for low pass filter and then band pass filters, but it is not best for designing the high pass filter and band stop filters. So with this, let me conclude. Thank you.